All right, first question. Who here works on performance engineering at their company? Okay. Okay, I got third. Okay, important question. Who here's favorite programming language is Rust? Okay, third. And what about C++? Okay, and what about another language? Oh, okay. We have a Rust leader on the stage who might have some opinions. Welcome, everyone. Yeah, we've got a super exciting lineup tonight. You might say a high-performance lineup, if you like puns. But yeah, I'm Will, CEO of Exa. We're building a search engine over the web. We're building it from scratch, which is pretty hard. And we use a lot of compute. So we partner with AWS to make this event. We use a lot of AWS. And we have some AWS people on the panel. Actually, we use everyone on the panel, now that I realize. We use a ton of AWS. We use Claude for everything and to power a lot of our stuff. We use Claude for coding. We use Modal for inference. We use Lance for our storage. So that's pretty crazy. Well, welcome everyone. So first we'll do the panel, and then I'll do some questions, and then you guys should prepare some questions or think of any questions you have. And then we got a talk from Shreyas from Exa, who built our vector database from scratch in Rust, and he has strong opinions about it. Okay, to start off, do you guys want to introduce yourself and talk about how do you think about high performance engineering at your company? Sure. Maybe go from left to right.
Can you all hear me? Yeah. Yes. Well, hey, thank you for having us. My name is Rohit. I am a member of the Foundation Model Training Inference team here at AWS. I've been with AWS for about 5 years, and we get an awesome opportunity to work with some amazing startups like yourselves and founders like yourselves who are building such cool things in generative AI. What was the question?
How do you think about high performance engineering at your company, at AWS?
So I'll talk a little bit about what something that we're focusing on right now, which we think a lot about how customers are building foundation models on AWS. And one of the biggest challenges that those type of customers have, you can think of maybe the Anthropics or the Stability AIs or some of these other foundation model providers out there, are how do they manage large-scale distributed training clusters? And I think if any of you have tried to train a model before and faced challenges with GPUs, this is something that's top of mind for many of our customers and us internally at Amazon. And so for us on our team, we're trying to figure out that challenge of resiliency within large-scale GPU clusters. How do we solve that challenge? Are there things around automated checkpointing? Are there things around training techniques that can actually be used to solve resiliency? And so we can talk a lot more about that in the talk, but I think that's where my head's at with performance and model training. Thank you.
Hi, my name is Chang. I'm the CEO and co-founder of LanceDB, the multimodal lakehouse for AI. I've been building data tools for about 20 years. I was one of the co-creators of the Pandas library, and I'm working on LanceDB today to help folks store and work with data that doesn't fit neatly into those Pandas data frames. And the way we think about high performance engineering is kind of three things. One is a lot of high performance starts with the right foundations at the storage layer. So if you are able to have the right data foundation for your workloads and the data that you're working with, you can essentially bust open the impossible triangle on performance. Number two is high performance optimization happens at a system level. It's not just about the coolest algorithm or the coolest language, but it's about looking at the workload, looking at what exactly at a system level is causing these performance bottlenecks. Could be the CPU, could be memory, could be I/O, could be something totally different. And so you have to look at it from a system level. And then number three is sometimes it's not really. Sometimes the performance that matters is not so much machine time, machine performance, but it's about human time. So the things that you're building, you have to take into account the developer experience, and are the developers using your system able to iterate quickly and build things easily and debug very easily. So those are the three ways we think about high performance engineering.
Okay, hi, I'm Daisy Hollman. I work on Rust at Anthropic. I have about 10 years of experience in programming language standards and such. I was involved in the C++ committee for a while, and then realized that I couldn't really do AI with that, and there's not a lot worth doing right now that's not AI. So, I mean, I'm kidding, but not really. And so, yeah, I moved into Rust at Anthropic, and I've been working on building out our infrastructure for that. How do I think about
Performance engineering.
How do I think about? Okay, so I definitely think about performance engineering in terms of developer experience. I think that developer experience starts and ends with quality programming language experience that gives you the right access and abstractions to the actual system, that doesn't confuse you, that doesn't mislead you. I think a lot of that design, and this really happens in library design, it happens in API design, although I'm being told, I'm learning now that I'm getting into this space that API design means something to do with REST, or I don't know. Anyway, API design I usually
Not
mean
MCP.
Yeah, MCP is mostly right. Anyway, so programming language focused is one thing I would say, and developer, really human experience, and then increasingly the agentic experience, right? How does the agent understand what it thinks the computer is doing via the programming language? And I think that is really the direction programming languages are evolving in the future, is efficient expressions of the system's behavior to the agent that's largely going to be doing the development.
Hey everyone, I'm Charles, and I work at Modal. We're a serverless compute platform focused on high performance computing. And I did a PhD at Berkeley on training neural networks, trying to prove they converge back in the 2010s, when generating a handwritten digit was the coolest thing you could imagine. And been sort of following the technology up the stack, as it's now something people want to actually, put out in the world. As the technology has become closer and closer to production, something people are actually paying for, something people are trying to optimize and put out in the world, in a competitive world, performance has become increasingly important, increasingly something that I've had to think about, and not just type theoretic correctness or algorithm construction. And so it's been a fun journey for me, and you'll be shocked to hear this, but I actually think performance engineering in terms of the developer experience. So where this shows up in Modal is that performance is basically at the core of our product, and that's for two reasons. The first is that we're this serverless execution, kind of remote. You want it to feel like remote procedure calling, where it's you call a function and it just happens somewhere else as a matter of implementation. You get the results back. It's a delightful form of programming that's 5 decades old. Mainframes, not abacuses. And with one of the reasons why RPC in the past has sucked is that it takes seconds to do something simple, or tens of seconds to do something simple. And so we did a lot of sort of very low-level work to custom file system, custom container runtime, etc., to make spinning up remote procedures fast, both and that the core of it was the developer experience of building against remote functions. You're working on something, you're debugging it, you don't want to oh, when I debug this part, suddenly it takes an extra 30 seconds or an extra minute. And then the second part, where performance ends up being core to the product, is that people are paying us for compute cycles, and any compute cycles that we waste, is something that they're going to get mad about. Our margin is, I think, your CEO's opportunity, and so trying to get rid of that sort of customers, our users respond really strongly to oh yeah, this overhead is removed. Here's how we optimize these pieces. Here's how we made it possible for you to run your code at the highest possible performance. And so in both ways, the performance engineering, not for strictly computer reasons, but for very human and economic reasons, ends up being at the core of what we do.
Hi everybody, my name is Venkata Sistla. I'm a senior solutions architect at AWS. I guess from a performance standpoint, what I do on a day-to-day basis is I break the storage services from an ML standpoint. So I take them to the brink, I test the limits, and then send the feedback to the service team so that we're able to incorporate that into the feedback and essentially make it better for you guys. So another byproduct of that exercise is when testing the limits, I'm able to also create guidance for customers at various maturities, saying, okay, watch out for these, and you have these mechanisms to work around in the current circumstance, and we're able to incorporate that into the product feedback and make it better for you all. So I guess very contextually, I break storage services in the remit of ML training. So I do distributed training across various ML frameworks, and with huge data set sizes, for example, test the limits of Amazon S3, FSX for Lustre, and really understand where the performance limits from a throughput and latency are. So I've recently published a blog around checkpointing strategies. So effectively, learning lessons from the last 6 months. It was a really dive deep exercise to understand how can you effectively, or what are the best mechanisms to do checkpointing read and write in terms of distributed training. So yeah, I guess that was a pretty fun exercise for me over the last 6 months, and I'll be on to our next exciting challenge after New York Summit next week. So yeah, that's pretty much it for me.
Nice. All right, here's a fun question. Can any of you tell a story, a war story, of a time when you had to optimize the crap out of a system? And please give all the gory details you can.
Starting with me again.
Anyone who has like an interesting story.
I may have a good one, but I don't know if it is going to set the tone for this discussion well. But so I got the opportunity back when I was in academia and working on the C++ standard as part of my work to work on multidimensional arrays for C++. For if anyone here has ever written C++, know multidimensional arrays are an absolute nightmare. They're very slow. They're very pointer-to-pointer things, and I got to work on the standardization process for the design that eventually went into 23, and the stakeholder surface of something as fundamental as a multidimensional array in a language as broadly used as C++ is just massive, right? Like, I think it was a really interesting. It was a really interesting exercise because there wasn't really a over-engineered limit, if that makes any sense. I think there was always like, oh, this use case needs to be addressed for someone, otherwise they won't vote for your proposal and it won't make it into 23, it'll be delayed to 26 and all that other kind of stuff. And so I think that was one of my favorite exercises of my whole career. The paper is MD-span. It's in C++ 23, and it provides all kinds of different generic abstractions for different layouts of data and different ways to access data. Maybe it's not even in local memory and things like that. And that designing those abstractions in a way that scaled with the way people use it and still worked in a way that was intuitive with reasonable defaults, and figuring out the defaults was a fantastic and really fun exercise. Yeah.
Sure. I guess my story is like, we were working with a vehicles company. I won't name the name, and the problem they were running into is just, if you're a vehicles company, you're collecting all sorts of data, time series from the sensors and images and annotations, 3D point clouds, and they wanted to do a bunch of scenario mining of like, hey, out of this data, how many times were there when the car automatically applied the brakes when it wasn't supposed to, with a bunch of criteria. And the problem they were running into was, well, their current system was running slower than real time, meaning like for every second of data they collected, it would take more than that second to actually like scan through that data. And so we had to kind of look at it like holistically from top to bottom. Is that the data was stored in protobuf, which was extremely difficult to work with in an analytics workload. The scripts were running in pure Python, right? So, and then the results were not being compiled in a format that was conducive to like further aggregation, right? So this was like a perfect example, kind of capture capturing the three ways we think about performance engineering. You have to have the right foundations. You have to be thinking about the whole system, like where the performance bottlenecks are, and then think about the developer experience at the end. I think what we ended up doing was something fairly simple. We converted all their data into Lance format, and this was actually when we did our first cut iteration of like rewriting everything into Rust. That was actually our Rust build moment, and then we wrote like this Arrow flight server to run SQL on the Lance data, and I think the project took us maybe like a week to do, and this was like in the early days when it was just LanceDB, and we ended up showing something. We benchmarked something like 9,000% improvement in performance. Not surprising, but like it's when the numbers came out, it was still kind of shocking for the level of effort that we put into that.
So I really liked what was said in the intros about developer experience and builder experience and building for developers. So how many of you have used a GPU before? Or how many of you had issues using GPUs before? It's very difficult. And then one last question. How many of you have had challenges procuring a GPU, getting access to a GPU? I think a lot of people, right? So at AWS, I think when we were thinking about no worries. So last year, I think we're in a place with GPUs where GPUs were very capacity constrained. And at AWS, we had many different customers that wanted access to GPUs that they may not have been able to have other sources or even sometimes within AWS. And it was hurting the builder experience because customers weren't able to actually build their generative AI workloads on our platform. And so one of the things that we set out to do was how do we actually make it easier for customers to procure GPUs on the AWS platform? And so we ended up going and looking at all of our internal systems that might actually block the procurement of a GPU. We looked at everything from pricing systems to even like the management console systems. We looked at the algorithms that look for available capacity in our data centers of GPUs. I'm talking H100s, H200s, the G instances, which are L4s and L40Ss. And what we ended up doing was we built a service in Q3 and Q4 of last year that actually launched at reInvent in 2024 that made it, the goal was to make it as easy as possible for customers to set up GPUs, procure GPUs, and get started with their training workload. That service is called SageMaker Flexible Training Plans, which is something my team launched in, as mentioned, in Q4 of 2024. And one of the things that we were really excited about was, and one of the things we heard was, how do customers actually set up large-scale GPU clusters quickly? This service actually allows you, as a customer, to set up a GPU cluster out of the box. With just a few clicks of a button or CLI commands, you can actually go end-to-end and set up a distributed training cluster with a distributed file system, the high-performance networking required for distributed training. And so when we think about performance engineering, and we relate it back to builder experience, we wanted to make it as easy as possible for customers to get started, and that's something that our team had launched last year. And so I think that would be what I would say here.
So I'm also going to take a slightly different tack on this question, like Daisy did, and instead of talking about the narrow performance engineering, like not loading time zone databases when you boot a container, which is a good trick. Instead, I'm going to talk about how I really learned what optimization means. In my PhD, I was studying neural network optimization. How do you prove that neural networks converge, right? How do you prove that they find the optimal value or one of the optimal values for the parameters, or something close to the optimal value? So you frame the problem that way. So you're saying okay, the algorithm I'm going to run is going to optimize a thing, right? And you want to prove that that thing is that thing works. So the mathematical framework people take is they look at how big are the gradients, because if you've made it all the way to the bottom, then there should be no more gradients. The gradient updates should be 0. So it turns out the way that you frame that is as an optimization problem. You want to say I want something that makes I want to see that the gradient norm is going to 0. So the technique that we applied to try and do some empirical work on neural network optimization was to take the neural network training process and do the gradient of the gradient, or specifically the gradient of the norm of the gradient. So we're saying let's find the place where the gradient is small via optimization. So that ended up pushing me out of PyTorch and into doing a bunch of things by hand, because they didn't have the second order gradient calculation at the time. And when you do the second order gradient calculation, you discover that it's this matrix vector multiplication. So you're doing this second order optimization. And if you stare at that for a while, it turns out that what you need to do is you need to invert a matrix. This is closely related to Newton methods for optimization. And so it's on a math, at a math level, you just write out invert the matrix, right? And then multiply by the inverse matrix. And so I was using that method and it wasn't working properly. And I was well, why isn't this working properly? Well, it turns out you don't just invert a matrix. Inverting a matrix is an iterative process. In the same way that actually you don't invert a number, there's an iterative process that produces the inverse for a number. So it turns out that is actually also an optimization process. And so it's framed, the technique is Krylov subspace iteration. But that is framed as an optimization process. And so I had to peel all the way down into that thing to figure out where things were broken. And it turned out the answer in every single case of the optimization problems being approached was that you don't actually optimize, you just satisfice, which is to say you just get to a point where the number is very small, and then you say good enough. So at the very bottom level, there's this residual term of how far away are you from actually inverting the matrix, and that was not always going to zero. And the further away from zero it was, the more likely it was that the whole process was being broken. And so that was part of the research result. The second was the gradient norm. Turns out it does not in fact go to zero during training, and sometimes it actually goes up. Leave that one to future work. But it there's also just I was trying to get it down to, I could get it down to 10 to the minus 100 to floating point precision or literally zero in certain cases. Turned out that was the wrong way to think about it. There were narrow cases where you could get to zero, but actually you wanted to set a cutoff and say this is good enough. And then finally, neural networks aren't really going probably down to the bottom of their lost landscapes. They're stopping somewhere along the way, and it's good enough to get a 50% on SweBench, and then you're done. And so my takeaway from that was the importance of satisficing rather than optimizing. Of saying what is the purpose for which I'm optimizing this system, so that you can tell yourself when you are done. So maybe that's interactive latencies of 400 milliseconds. Maybe that's your 1 second tick for data collection. But whatever it is, it's to save your sanity, you have to find something that you can call good enough, even if you're just doing something that's pretty close to pure mathematics.
I don't have any cool stories as the rest of the panel shared, because I just break stuff. Pun intended. But I think just to extend what Rohit has said, when they solved the procurement challenges around GPU capacity, what as a side effect has led on is they have enough GPU capacity now, but in the regions where they're able to procure GPU capacity, we are running out of storage capacity. So I guess we are now solving through in terms of how can we accommodate both, and it's an interesting challenge or an optimization exercise within the organization. Another side story has just kept me a bit more curious was during the exploration of checkpointing efficiencies, I came across a term called good put. How many of in the crowd have come across the term and have the understanding of a good put means? Okay, we have one. Cool. I'm also still learning, so I think good put is a good measure of efficiency, especially in the world of distributed training and around compute and storage performance. So yeah, I guess Google has established that term officially in terms of the measure of performance, and Yeah, since then I've embarked on the journey of understanding the, I guess, the relevancy of Goodput in terms of measuring storage performance and how can we make our storage services, like the offerings from AWS, in line with the definition of Goodput. So yeah, that's pretty much it for me.
Cool. I have one more question for the panel, and then I'll open it up if you guys have questions for specific people. So think of your questions. But here's another fun one. It's more about a vision. Imagine you had 1,000 years to work on some part of your system that you really care about. How optimal could it get, and what does that look like? And just as an example, at EXA we're building a search engine, so I think if the engineering team puts in enough effort, we could probably get our search down to like 25 milliseconds. I know that sounds crazy, but and if we have have enough customers to amortize the cost over. And on the accuracy side, I think we could basically get the perfect search where like every search gives you exactly the information you want. Those are two axes that we care about, and I think if we had 1,000 years, we could definitely do it. We don't have 1,000 years; the space is moving too fast. But for example, with Modal, what is the vision of what is perfectly optimal if you have enough time? And then same with Anthropic and all your companies.
Yeah, just point of inquiry, is this like a hyperbolic time changer, go-through rules, where I go in for 1,000 years and then I come out and no time has passed?
That's right.
Okay, all right. Yeah.
Thought it was obvious. No.
Yeah, no, that one's tougher because it's you probably can't put together a fad in the hyperbolic time chamber even with 1,000 years. If you think about Tom Hanks in Castaway's technological progress, it's pretty fast but not that fast.
You also, your whole team gets to be in there too. So
Whole team gets to be in there.
That matters.
Okay, off-site in the hyperbolic time chamber.
And you have the internet available to you.
Yeah, okay. I think the thing that we would optimize is basically cold booting, which is another way to say sort of state management and state sharing and caching. So yeah, we're a serverless platform. People want to be able, and the thing that makes it slap is that when a request comes in, if there's not a GPU ready to handle it, we get another one ready to go in a few seconds. And a few seconds is pretty fast on some objective time scale that bottoms out at Planck seconds. It's pretty fast on a time scale of it's actually slow on that time scale. It's pretty fast on a time scale of racking and stacking new hardware. But the scale on which it's slow and that is bothersome is getting in the hot path of responding to a user, right? You guys are talking about 25 milliseconds for your search. That's the time scale that people want to operate at. I mean, obviously you would prefer to move at 0 milliseconds per search, right? Yeah. The mycelium spore drive of searches, which is the fastest drive in the Star Trek universe. You go anywhere to anywhere instantly. It's warp infinity. Anyway, it's in the NVIDIA way, the Jensen book. Read it. Yeah. So that is what you would want. It's not possible. You have to satisfy it at some scale. And getting cold boots down faster, a lot of it is about being able to pre-compute state, store it somewhere, and make that process as transparent as possible. So the most recent place where we've made progress is on snapshotting GPU memory state, so that you could, for example, spin up your LLM inference engine that creates some state in the GPU, some state in the CPU. Right now, with the current state of technology, it seems like it's just a bunch of bytes, so you should be able to just toss those bytes in some kind of storage and pull them back out. But you can't, because some of those bytes represent live resources that are not amenable to being frozen. And so there's a little bit of surgery involved there. And that is what has taken folks like NVIDIA and other people time to try and put together something that can truly do that kind of checkpoint and restore. And just watching that process and seeing how fiddly all those tiny details are has made me realize, how much of sort of compute we are wasting in a lot of other places where it's actually just hard to really define what it is the state is that you are creating. And storage is free, right? And infinitely scalable is my understanding. Yeah, so or at least they had pushed that far enough that I could, if we sat in a chamber for 1,000 years and worked on just that kind of caching, state management, and restoration, could turn around and have a bunch of machines that boot in milliseconds for every program that people want to run. And then maybe we come out and find that we'd busted the scale on storage and be time to pass the hyperbolic time chamber to y'all.
So basically, like instantly scalable compute is what I'm hearing. Yeah.
Yeah, and a good segue is I would essentially create like an abstract layer where you don't no longer need to think about what's like storage type, whether it's an object, file system, what to optimize, cache. You just throw your data volume, any data type, it will figure itself out, and it'll probably be free.
Wait, it's like storage or compute or anything? Or what does it do?
I'm calling it like a membrane sort of a concept. So where it's your application can just interact with that abstract layer, and the abstract layer will figure out all the storage complexities. In terms of partitioning, best practices, how to organize your data, metadata, figure out the throughput.
Ooh, that's really exciting. Like, yeah, why should I have to like select how much storage my volume? Like, it should just figure it out. It should scale up and down when necessary.
Yeah, because these problems are very prevalent today because storage is an afterthought. So you would go and figure out a use case, you would start building and then say, hey, I've hit the bottleneck, and where is the bottleneck? And then you would reverse back and then you figure out its storage. So especially it's more and more happening in the case of distributed training or traditional ML. So which is where our guidance as solutions architects from AWS is saying, can you proactively plan your storage? So we're creating guidance around, do you know object semantics versus file semantics? Do you know the differentiation between both? If you go down the object path, then you'll have to build your integrations yourself because the application layer doesn't know how to interact with an object store natively. On the flip side, if you bring in a high-performance file system, it's much more easier, right? So there are nuances and complexities around storage too. Yeah, I guess I would definitely make that simpler going forward. So because the customers that we see, day-to-day basis are facing those challenges. Yeah.
Cool.
So, I mean, I was going to say that I'd like to hit 100% on Sweet Bench, but I think we need maybe 3 to 5 months for that, not 1,000 years. And I was going to say I'd probably deflake our CI, but I think we need more than 1,000 years for that. So, but no, I mean, in some seriousness, I do think that at least in Anthropic, there's a lot of focus on hitting the point of exponential return as we close the loop. And I think that applies to performance engineering as well. I think it's very important for us to get to the point where our agentic tooling can do efficient performance tuning of GPU kernels and things like that on par with what a senior or principal engineer can do by hand. And I think if I had 1,000 years, I would absolutely prioritize that, although I think we'll be there in 6 months to a year. I don't think it's very unreasonable to think that these sorts of kind of fiddly flop shaving problems will be things that AI agents are better at than humans pretty soon. And I think figuring out what development environments look like in that world, figuring out what workflows look like, figuring out what an engineer's day looks like, and figuring out how we rapidly improve software and rapidly improve performance and performance environments in that space is something we haven't spent enough time thinking about. Like, what is the developer experience when an agent is better at optimizing on the flop level, low-level kernels, GPU kernels, and things like that? I think it's a very interesting question that we should be asking in developer experience spaces right now.
Yeah, I would love to have it be better at Rust code.
We're getting there.
I mean, I would just say, Will, you can probably empathize, but as a CEO, the prospect of locking my team away for 1,000 years and not violate labor laws, that sounds great. So if anybody's working on that hyper time chamber, let me know. Yeah, I mean, I think, like, personally, we started working on the data format because of all the weird trade-offs that, something like a Parquet forces you into, right? You have to trade off on the row group between like large columns and small columns. You're trading off between like random access versus scans and a bunch of other stuff, right? So the thing I would love to have, and it won't take 1,000 years, is like, Lance will be a format where it has, constant time random access, like much faster scans than Parquet. And for every data type that you store, it automatically has the best, most optimal compression ratio, right? So the smallest file possible, right? And then I think on top of that, it's about the workloads that you do with the data, so that like working on this like 10 petabyte, video, image, metadata mixed in kind of data set still feels as easy and as fast as like an in-memory, pandas data frame with like 100 rows or something like that, right? That, like, to me, that'd be the dream for working with data.
Do you think we could get like another 9,000% speed up in like handling 10 petabytes? You know what you're talking about? Like, what kind of, like, how far from optimal are we?
Oh, I think there is a speed of light somewhere, but like we're not that close to it, like as an industry.
So we have 1,000 years?
Mm-hmm.
Okay.
With the whole team, it's like 1 million people at AWS.
Yeah.
It's a good party in there.
A lot of building going on in that 1,000 years. So one of the things we're super excited about in the future is the idea of artificial intelligence and robotics and physical AI at Amazon. And it's been amazing to see some of the progress, even in just the last 2 to 3 years, this movement, or I guess this phase change from like purpose-built models for different tasks on a robot versus now companies, startups are building foundation models that work on more generalist tasks on robots. And I think you can see the work that NVIDIA has done with Cosmos Reasoning and NVIDIA Groot, which is a model that they built for humanoid robots as well. Skilled AI, physical intelligence, Covariant, which is now part of Amazon, who built a foundation model for warehouse operations and warehouse brain. It's been amazing just to see that progress. But one of the big challenges in foundation models for robotics, or a generalist foundation model for robotics, is that there's a latency challenge when those models are run not at the edge, when those models are not run on the robot itself. And the reason that those models can't be run on the robot right now is that the GPUs that are usually running on the edge don't have the GPU memory requirement required to host that reasoning model or that foundation model itself. So if I had 1,000 years to build, I would hopefully build towards a ChatGPT moment for robotics, which I think will be when generalist reasoning models will actually be able to sit on the edge, on one of these edge GPUs that sits on the robots. And so how do we increase the parameter count, or how do we make these models more efficient to actually fit on these edge GPUs?
I always wondered why can't it be like in the same room like the GPU and then it communicates by Bluetooth or something?
Wish I knew. It's something we can explore in 1,000 years, hopefully.
I hope in 1,000 years we would have something better than 22.
Yeah.
Okay, cool. Well,
And by the way, if anyone's working on a robotics or physical AI startup, please come talk to us afterwards. We're super interested in learning what Amazon can build for these type of startups as well. So please let us know. Thank you.
cool. Well, if these are all software problems and Claude actually makes us 1,000x coders, then we actually could get it by 2026, everything you just said.
Yeah.
Well, cool. Does anybody have any questions for the guests? And don't hold back. Give them the hard one. Vijay?
So I guess one of the things you guys mentioned like just now was about how you want to be able to optimize, say, like a model for robotics or a model for the performance of like different pieces of software like GPU kernels and whatnot. Do you think all of this sort of stuff will rely on the big LLMs that we have trained over the web, maybe even like fine-tunes of these big LLMs that are trained over the entire web? Or do you think it will be more like you have individual models that are trained from scratch on these different kinds of tasks that we give it?
Let's do quick answers here also so we can do a few.
Yeah, who's familiar with the bitter lesson? Okay, yeah, if not, you should Google it. The basic idea behind it is that the economies of scale behind general models typically win out over specialized models, and we see it over and over and over and over again in AI. It was 2019 when I think the original article was written, and we've seen 10 major notable examples of it since then. Like text and image generation was one of the most recent ones where the general models just caught right back up. So yeah, I think these will all be mostly from general models or fine-tuning on general models. I also think thinking about this thing as being trained on the whole internet is at least 6 months old, which is years. I think we'll probably be in a few years 1,000 to 1 RL to pre-training. And I think, so thinking about it as what do you want RL for is another answer I would give to that question.
Yeah, I think I would maybe dispute your characterization of the bitter lesson.
Okay.
Which is a fun and spicy fight we can have.
Yeah.
So yeah, you said it was about general models beating out specialized models, and that's definitely true. And I trained, I taught people how to train a text recognizer model that's now handily beat by any of the foundation models. So that is a lesson I have learned, and it is bitter. But I feel like the bitter lesson is that techniques that scale with compute beat out techniques that don't scale with compute.
It's a better characterization. You're right.
Yeah, and it's the reason why I think that's interesting is because he talks about two ways to do that. One being learning, because learning just scales with data, and you just throw more data at it, and you put more parameters in the model, and think it's better. And then the other side is search, right? Which is you produce a bunch of candidate solutions, and if you can evaluate them, then you just throw more compute at either generating the candidates or generating higher quality candidates or generating more candidates, and you can select them. So on both of those, I feel maybe there's capacity limits of small models or limits on our ability to collect data for specific domains that mean that better lesson applies more to general models. For search, if you're doing search at the edge, having a smaller model means you can maybe run you could take an 8 billion parameter model and run that thousands of times in the time that it would take you to generate one candidate from an 80 billion parameter model. And there's at least, at the current stage that we're at, there is some ISO flop and there's some ISO flop results and others that indicate oh yeah, that actually turns out to be better. And so then you want something that can fit in that amount of memory, which maybe involves throwing out a bunch of that existing, the knowledge that would otherwise be in the weights with a large model. I guess, I don't know. Do you think I'm missing something that means oh yeah, it has to be this generalist foundation model that is doing the search or that goes out to the edge?
I haven't been in AI long enough to really believe the bitter lesson. So I'll be honest, I think MOE is starting to be a breakdown of the bitter lesson, kind of, in a sense, right? So I don't know. I'll let other people say things.
Cool. Any other questions? Oh, you got it.
Well, I just had a small thought on that is one of the things that we hear from customers a lot is how do they get ROI out of their investment into generative AI? And from a technical perspective, one of the ways that we could reduce the amount of costs that they're spending on generative AI is reducing the model size that could be specialized on a specific task, as those models are going to be running on smaller GPUs. And so one of the I guess activities that we do with large enterprises or any of our customers is walk through all of their use cases, and we do identify what types of models could be used instead of the largest models that might take maybe two H200 does to run in distributed inference versus maybe a smaller specialized SLM for that could run on a much smaller GPU, and that ends up being the tokens per second significantly cheaper, as long as their use case and their business case is solved for. So that's one of the ways that we would look at it. But generally in the future, maybe these large frontier models will get computationally efficient enough to be able to achieve those tasks at a place that businesses are willing to invest at scale.
Sorry, it's been thinking. So yeah, so if you think about it, the best way to solve any problem is an ASIC. And so any problem that sticks around for long enough, somebody builds an ASIC for it. So in the 90s, it was very hot to use a Linux machine as a router, and now that is not a thing that is done nearly so much anymore. And there's also refrigerator-sized machines living at internet exchange points that do a bunch of routing, and they have components of internet protocol and TCP flash directly into the hardware for stripping bits and mapping them around. So I feel the fundamental answer here is that when you have a specific capability or affordance that you want out of a system, eventually the answer is going to be some fairly specialized system. I expect it to be distilled out of a large scale model that gives you these super high quality logits to train off of instead of janky human labels. But still the thing is this compiled artifact. And so I would expect that to be, the Amazon Go stores of the future aren't going to run a little Claude instance in every camera, right? They're gonna run some small computer vision model to extract signals that may go back, and the overall system involves generalized things, generalized models, general purpose computers, extremely wasteful things all software running on generic computers is incredibly wasteful. If you were to just take that DAG and turn it into transistors, you could do it more than 9,000% faster. Yeah.
One.
Okay, we got a lot.
Right now, we talk about GPUs and TPUs as kind of being the big bottleneck. How long do we see that situation continuing for? And what do you all think will be the next big bottleneck after them?
That's the last question, so I haven't really good answer.
Can I ask you a question about that? What do you mean by bottleneck of GPUs and TPUs? It could be a number of different things.
So, in my work at least, we think about limiting, you need to make a lot of LLM calls or for inference or for training. For example, with Meta, one of the reasons when all this talk about, $100 million buy-away contracts is that they're also throwing in, hey, TPU time or GPU time is so limited that we're also offering it as something that we can use to hire you as much as a scarce resource. What do you see as, if that eventually gets resolved, what's the next thing that everyone's going to be desperate for?
Got it. The question was about the next big bottleneck.
Yeah.
Okay,
Yes.
Understood. So definitely something that we hear at scale, and what we sometimes face here internally, is around the data aspect of models themselves. Right, I think Ilya had a talk recently, maybe about 6 months ago, where he talks about data being the next frontier, the data being the biggest challenge of what these models are going to be trained on. And so, in my view, I think, and we were even talking about it before the talk, about how do we break down enterprise data silos and actually get access to data that these models might not be trained on, that might make them smarter and help customers make better decisions when they're using these models as well. So I would say access to data would be something that would be a frontier that would likely be needing to be solved. In terms of the compute part of the first aspect, I think there's a lot of challenges with compute, and there continues to be, from both an access perspective as well as how computationally efficient that these GPUs are as well. And so I do think that there's going to continue to be a number of startups, a number of companies that build specific solutions trying to solve this frontier as well. And it's something that we see consistently, and something we're working on significantly as well.
I can add. I just want to add a little bit. In terms of the GPU utilization, what I've seen is customers realize that there's GPUs are costing more and it's actually getting more expensive. And when you dive a little deeper and then peel off the GPU layer, it actually takes you down to the storage inefficiencies and not being able to understand the underlying storage configuration and what you're expected to get out of, and you just throw a default config because storage was never a main concept anyway. So the inefficiencies around the storage layer are continuing to keep GPUs idle, and creating you a lot more expensive bills from a compute standpoint. So from an overall training optimization, it's a collective effort, but the storage is going a little unnoticed, and we want to bring that sort of education planning upfront so that you can better take control of your GPUs and get the better outcome for what you're paying for from an infrastructure standpoint.
Okay, sorry to cut this off. I know we could talk about this stuff for a long time, unless you got quick answers.
Yeah, so the bottleneck is like more power and data centers than it is like literal cards, right? And I think we're like effectively mobilizing resources at like a global scale to solve that problem. And I do agree that data is likely to show up as a bottleneck in the near future. But if you look a little bit further out, and if you were listening carefully when Daisy was talking, the future is 1,000 to 1 or more ratio of RL to data. And so there, like, yeah, the compute shows up as a bottleneck again, because now you need a whole bunch of extra compute. But the real bottleneck there is reward functions. The bottleneck is hills to climb. If you want to make a 1000x doctor, you can't just like throw the model into a hospital and say like, please figure out how this works. That barely works with people. It's not going to work with language models. So actually, like the incoming bottleneck, and the Andon Labs people who did the Claude Venn project with Anthropic are working on this specifically, is trying to construct optimizable things to throw these systems at. And I expect that to be like one of the critical things people work on in the coming like decade or two.
I think, can I say something real quick? I'll be quick. I think we're like, to answer both of these questions, I think we are one transformer level breakthrough away from steady state, at least one, but I think one for sure, away from steady state of AI. And I think whatever that breakthrough is involves a much better understanding of plasticity. And I think in that world, you're going to have much more specialized models growing out of whatever that expression of plasticity is, and you're going to have bottlenecks that involve not just data, but weights storage. And I think that is something we haven't even started to think about really as an industry.
Cool. All right, everybody. That was a great panel. Let's give it up for them.